Good afternoon. My name is Kenji Rikitake, and I'm going to talk about an implementation of RNG called Xorshift star, and how it's being implemented in Erlang OTP, and general random number tips on the Erlang programming and other maybe applicable to other programming stuff. Okay. I was doing the HCM Erlang Workshop 2011 chair. And I've been here for 6 consecutive years, and this is my 6th year to be here, and I'm very proud to be here and talking to you. This face is rather surprised about. This is real me. This is just photograph. Okay, the executive summary. When I make this kind of talk, it's always the same, but do not try to invent your own algorithm, especially on random numbers or cryptography. Don't do that, otherwise you're in big trouble. So, why PRNG? Okay, I use PRNG for pseudo-random number generator. Just remember PRNG. It's really hard to pronounce a pseudo-random number generator every time. So, why PRNGs matter? I made the first talk of PRNGs in Erlang Factory of 2011. And at that time, I was talking about SFMT, an implementation which I'm going to talk about later. And I proposed there that random modules, random number algorithm is kind of weak then. And it's 2015 now, 4 years later. And unfortunately, people are still using the old implementation of the random module, which is actually fully exploited. Not only by me, but I could exploit within the 9 hours. I'm going to talk to you about it later. So what I would like to tell you is that we should stop using it now. I'm trying to convince the OTP team. And there's at least one supporter in the OTP team who is kind enough. His name is Dan Gudmundsson, and he's a very experienced code writer for Elang. And he and I been working together with a new implementation. But anyway, so I decided to do the talk again, and it is accepted, so I'm going to talk about random numbers. Okay, PRNGs are everywhere. One of the audiences asked me about using random numbers on game, which is actually rolling dice. And I've heard that there's a random number generator actually rolling dice with a machinery and taking the photograph every time and converting to the real number, real integer numbers. But that is too slow. So people want to use the computers and a more faster algorithm. And there's another important application of random number called property testing. Property testing has a lot of aspects, but one of the aspects is that you put so many different random kinds of parameters into a function so that the function goes crazy, or functions just handles the error properly or something like that. There are at least 3 major tools: quick check, proper, and trick. Those stuff are all doing the property testing and use the random numbers very effectively. And I'm going to explain this in the next slide, but there's an actual application of entering randomness into the input and observing the randomness coming out to the system. One of those is that variation analysis of electronic circuits. Electronic circuits are not necessarily linear. Linear means easy to analyze. It's sometimes very complex. So the only way to analyze is often you have to change the input and observe the output. And there's another stuff like that especially for the network management. It's about network congestion and delay analysis. And there's a utility in FreeBSD which artificially drops packets randomly or artificially delays packet for a certain period of time, which can effectively simulate the network trouble, which is very convenient and useful. And for the real-world business, risk analysis of project schedules is often conducted using random numbers, adding random risks, the schedule delay, or kind of damages affected by the lots of incidents, or whatever. And there's another important application. It's about generating passwords. But for generating passwords, don't use the algorithm I show you in this presentation. Use the secure PRNGs only. Only secure ones, please. Or otherwise, you'll be in big trouble. OK, let me explain variation analysis of a bandpass filter. This is an electronic circuit which has a 6 component, 1, 2, 3 coils, 1, 2, 3 capacitors. And if their actual values are as designed, there will be no need for random number analysis, or let's say variation analysis. But in the real world, you won't be able to have the actual value of those components. They will almost always be having some sort of offset between the given value and actual value. So if everything is designed, the shape of this is frequency and this is level. And what I show you is about the voice filter, so that cutting the lower part of the frequency and the higher part of the frequencies as designed. And without variance, you don't have to worry about how parameters are really changing. But when you actually make the circuit, you have to allow some percentage of variance, maybe 1%, 5%, or 10%. So let me show you the simulated result with the 10% variance. Actually, this is the cumulative result of drawing many times of plots overlapped, just overlapping the plots. It's so simple, but the important thing is that the cutoff frequencies varies, not so much in this case. But in some complex circuits which uses feedback or positive feedbacks, it will cause some disastrous effect. So this kind of simulation is necessary when you not just design an electronic circuit, but make a real product to sell, because you cannot have the design value of the part after all. So to make it show, this is a property test of the hardware. So we're going to do something, you have to do something like this on the software too. OK, next topic is about how PRNG works. It's quite simple. It's most PRNGs are designed as iterative process of for example, when you give a seed number 1, it computes, put it into the function, let me say it, PRNG, and it gives the state, it gives the seed change to seed 2 and result 1. And when you give the seed 2 to PRNG, it gives the seed 3 and result 2. This is a pure sequential iterative process. So it's really hard to make this computation parallel consistently. Some people, I've heard some people have invented so-called counter-based random numbers. Actually, it's like it's not giving a seed, but it gives a number. Number 1 of the result, number 2 of the result, number 3 of the result, 4, and 5, and 6. And so it's a sequential counting PRNG. But that kind of PRNG algorithm is still not popular. You have to deal with the internal state, and you have to put in the internal state and get the output state to step into the next step. So if you think about this, you have to be very careful for running multiple processes simultaneously on the same algorithm. If you do not carefully choose the seed, the output parameter, the output sequences will overlap with each other. And that may affect the result of simulation or what you're going to do very much. And one specific thing for Erlang, which I didn't describe in the slide, is that random function, or the old implementation I introduced in this presentation, uses the process dictionary, the evil. So the random number belongs to the process. So when you generate the process, new process, you have to seed the random number. Random numbers are, the internal storage in the process dictionary. Otherwise, it will be a lot of trouble. Okay. So I'm not going to talk about secure PRNGs in this presentation. It's solely designed for password and cryptographic key generations with strong security. And presumably, mostly from the physical random number generator. It's really hard to obtain physical randomness because you cannot predict them. You cannot compute them. You have to get them from the actual physical phenomena, such as from semiconductor diode, or sampling the ambient noise, or maybe the ionospheric noise, or whatever. But those are very scarce resources, so do not use secure PRNGs so much. Don't waste them, please. And for Erlang, almost always use crypto strong-rand bytes /1 only. And because this is a guaranteed, entropy guaranteed random number generator API for OpenSSL. If you don't believe in OpenSSL, you can invent your own. But OpenSSL is, I think, still far reliable than me. So, okay. I'd like to emphasize again that the randomness, I use the word entropy because it's a technical term for the randomness. Entropy gathering takes time. So if you use 1,000 byte of the secure PRNG, you have to wait for certain amount of time. It could be 1 millisecond, or it could even be 1 second if in the worst case. But it depends on the operating system, and it behaves absolutely differently between the Linux or FreeBSD. But anyway, it takes time. So if your random device blocks, that would be, you have to wait. And once again, this is cryptography, so use and only use proven algorithms. Okay, so in this talk, I'm going to talk about non-secure PRNGs. These PRNGs may be vulnerable to cryptographic attacks because of the many characteristics those PRNGs have. For example, they are predictive, totally predictive, give the same seed, same result. But this is also a necessary characteristic when you use the simulation. You don't want to expect different outputs on every simulation. And for the testing purpose, when you want to have the same output for the same input. So this is the necessary characteristic. And in most of the implementations, the output is in uniform distribution, which means that all values output have the same probability with each other. And non-secure PRNGs usually have a lot of internal state choices. It may be 64 bits, 128 bits, or 1024 bits, but it's fairly long for the actual use. And but mathematically saying, these PRNGs are not an infinite sequence. It's a sequence with period, although the period is very, very long, so that there would be no intelligible patterns. But in the real world, non-secure PRNGs often fail. Those failures could be found from the observable patterns by making a graphical representation, or can be proven from a very short period of showing up the same number sequence again, or brute force exploitation of computing all the possible results of a PRNG sequence. Okay. This is one of the failures, well-known failures of PHP 5 on Windows, not on Linux, I've heard. But see these lines and see these arcs. These are the visible evidence that this PRNG is flawed. Okay? There's another PRNG failure, which I discovered in 2013. A game maker called CryptoCAD wanted to do something like this. This is the output of dev-urandom, which is a sort of proven strong PRNGs in the world, either the world of Linux or FreeBSD. But by changing the counter value from 249 to 250, they made something like this with grid patterns and of the repetitive stuff, and this was considered a serious bug, and they had to withdraw the implementation and change the implementation. So when you implement PRNG by yourself, please do test them. If you have to, test them. If you don't have to, don't. Okay, and our OTP has, I don't want to criticize anybody in OTP team, but an embarrassing story of the first ever security advisory was about PRNG. ARM people, for some unknown reason, used unsecure PRNG, namely random module, into SSH library's key generation. And this was found by the very talented engineer whose name is Jeff Kant, and he thoroughly described how to exploit the whole stuff in this US vulnerability report. I like you to read this once, and this is so astonishing how easily people can exploit such a thing. And now this bug is fixed, since this bug was in 2011. And I think people developing Erlang OTP is getting much more wiser than them. But anyway, if you are using unsecure PRNGs for security purpose, the result will be disastrous. So don't do that, please. And there's other Erlang random number problem in Erlang, which has been known for so many years, but nobody is actually talking about this many times, is that the algorithm being used in a random number routine called AS183 is actually old, designed in 1980s when 16-bit computers was invented. And the creator of the algorithm specifically said or wrote that it's for 16-bit computers. And actually, the first algorithm it was appeared into the general public was in the Byte magazine. Do you know Byte magazine? Maybe many. Oh, okay, you know. Then you know what the microcomputers are. It wasn't personal computer at then either. Okay, stop the folklore anyway. All right. The period of the sequence generated by the AS183, I actually brute forcefully computed all the numbers in a very fast way using the modern computer called Mac Mini, and the modern Core i5, and it took only 9 hours using single core to exploit 7 trillion sequences. it's about 2 to 43. So 2 to 43 is not enough, even for the non-secure use of random number generators. And one of the very talented Erlang people, Richard O'Keefe, criticized me that I was doing nothing new in either academic or engineering perspective. Nothing. He completely hit me. And of course, I know. I accepted that. I accepted 100%. And I know he didn't criticize me because he also wrote me that you are trying to spread new algorithm. That's good. And that's wonderful. And it's really hard for everyone to get the word wonderful from him. But he's absolutely right. So I'm doing nothing new for this. Nothing new means this is so trivial that everybody can do it. So what I've done, let me get into the things what I've implemented, not invented, but implemented. Inventors with those algorithms should be respected much more than I am. But anyway, these are 5 algorithms. Number 1, SFMT Erlang, which I presented in the ACM workshop 2011 formally, and also in Erlang Factory SF Bay in 2011. And it has a very long period, 2 to 19937. Absolutely long lengths. I think it's physically meaningless of having this long period. But mathematically saying this is true, and this is proven by the 2 mathematicians. I'm proud to say that two people are both Japanese, Professor Matsumoto and Professor Nishimura. And SFMT is also designed by another talented Japanese person called, his name is Saito, Professor Saito. Okay, and Saito and Matsumoto invented another short period type of an MT algorithm called TinyMT, and this was presented in 2012 Erlang workshop. And today I'm going to briefly talk about these EXS stuff: Xorshift star 64, Xorshift plus 128, Xorshift star 1024. These star and plus stuff are the algorithm properties, and Xorshift is the name of the core algorithm. And these algorithms generate 64-bit output, and the period is kind of trivial because if it has the number 64, the period is 2 to 64 minus 1, 128, 2 to 128 minus 1, and so on. Okay, about SFMT, the MT is an acronym for Melson Twister. There's a superb mathematician called Melson, and he discovered that certain numbers 2 to a prime number minus 1 will be a prime number. And there's a contest of finding out the largest prime number in the world every time, and almost all of these numbers are Melson numbers. So Professor Matsumoto, one of the inventors of Melson Twister, put his name on what he invented. And it's default PRNG on Python, MATLAB, C++11, and R, and I think it's also on Ruby and everything. So it's quite proven, I think. And its internal state has 624 32-bit numbers, or better say 2,496 bytes. So the internal state is huge. But the algorithm itself works in this way. You first calculate the internal state of the whole big internal state, and output a chunk of the internal state, I mean 32-bit every time, for 624 times. And if all the chunks are output, the algorithm calculate another batch of the internal state. So this is how SFMT works. So Okay, and SFMT, why SF means it's for shimmed-oriented fast mouse and twister. So it's an algorithm improved from the original mouse and twister. And I've told you many times, but it has an extremely long period of 2 to 199.37, and even longer period versions are available if needed. And you can find it in my past, how do you say? In my GitHub archive on the past, past tag, or how do you say, anyway, history. Okay, SFMT Erlang gains a lot by NIFs because it needs bulk state initialization. So it has to calculate 624 32-bit numbers. And NIFnizing this will be making things much faster. I measured very briefly that and on the FreeBSD machine of Core i5, and state initialization, or better say batch generation, was 100 times got 100 times faster between the pure Elang and C. But when you measure the total generation time, including the generating the chunks from the internal state, the speed gain is much less than 100. It's only 16. This is presumably because the chunking of the big numbers is done in the pure Elang, because making it a NIF is making things more complicated and gains nothing. So making it using a pure Elang and with lists actually made things much faster. Please refer to my SFMT paper or SFMT presentation, which is available for my own site, my own website. You can ask me the URLs later. Okay, and the other one is called TinyMT, and it's called Tiny Mouse and Twister. And the period is shorter, but sufficiently longer than random module, 2 to 127. And the good thing about this is that internal state is very small. 4 32-bit numbers for internal state, plus 3 32-bit numbers, which explain the polynomial of the TinyMT. And by choosing or pre-calculating the polynomial, you can choose up to 2 to 56 choice of orthogonal polynomials. Orthogonal means completely different number sequences. So by using these characteristics wisely, you can generate the unoverlapping sequences for each process, especially for parallel computing. But I first made NIFs and no-NIFs version of this. But I eventually threw away the NIF version for the reason described in this slide. Because TinyMT does not have bulk initialization. It computes every time of the internal state from the given polynomial and other internal states. And the state calculation complexity is small. So even if you replace it to a NIF, you don't gain much. And most of the execution time of TinyMT was function calling overhead. That's what I've got from the fprofing whole stuff. And in NIFs, and in comparing in NIFs of TinyMT and SFMT, SFMT was faster for some strange reason. Or better say, I should conclude that the overhead of the function calling is so big. So I decided to put out all the NIF implementation about this and let the users suggest to use the non-NIFs version. So why NIFs so are NIFs effective, or are NIFs necessary for random number generation? I have to conclude, not really. Not really means if you generate lots of number sequence at once, means which means 10,000 times or 100,000 numbers of sequence at once, you will need NIF, and that will be effective. But there's a side effect, actually an adverse effect of NIF, that NIFs block the scheduler. So when you spend 100 microseconds in NIF, Beam scheduler can't do anything, any other things. So that will be a huge problem when you handle or juggle lots of processes simultaneously, like in the database software like React or RabbitMQ, queuing software, or other stuff. So the rule of thumb is that if NIFs are not needed, don't use them. I think this is common sense among our own programmers. But the reality is kind of tough, and you have to make the fast programs. So if NIFs are really needed, you have to tune the scheduler, and that is almost always inevitable. And don't ask me about that, please. Ask someone else, like Lucas Rawson or Scott Fritzy. They are the real experts. I don't know if they can design the algorithm, but they observe profile, and get to the reason and change it and may get the things work. So Erlang scheduler is so complex, so don't take it for granted. Okay. So what is Xorshift? Xorshift is originally invented by the mathematician called Massaglia, and he suggested that scrambling the output of Xorshift will be making the RNG much better. Better means will be resilient to the stronger pattern tests. So another mathematician called Sebastiano Vigna, he invented, and he not really fully inventing, but he calculated and tried lots of patterns of parameters of scrambling, and got to the result of the three principal algorithms: 64 star, 128 plus, and 1024 star. And according to his evaluation results, these are showing much better result than SFMT or TinyMT under the test called test U01. Okay, so I am not a mathematician, so I cannot 100% guarantee that this result is correct. But I think I can trust these people. These people have already released their own papers, and these are publicly available. So please read them if you are interested in. And the good thing about Xorshift star and plus is that those C pieces of code is in totally public domain. So no licensing issue. And they are deceptively simple. Let me show you the Xorshift 64. Only 5 lines. That's it. R represents 64-bit internal state. And remember that R is not directly used as output. R becomes R1, R2, and R3. And R3 is the new state. But the output is scrambled with just multiplying this, I don't read it, strange kind of number. But this works very, Sebastiano Vigna says this works very effectively. And Xorshift 1024, this has 2 steps. Number 1 is about 6 lines, which uses 2 pairs of 64-bit numbers into one state, one output state, and one random number generation output. And the algorithm uses a sort of a ring buffer structure. In C, it's much easier to write. You use pointer and the bit and the pointer value from 0 to 15. But that is not good on otherwise. If you try to use the array library, I'm not saying you're in trouble, but what array is doing is actually handling a lot of tuples. So I don't recommend that. So what I invented was using 2 pair of lists to simulate, or better say implement, a ring buffer-like structure. I'm not going to explain this code. You can just test run with this code and how the pair of lists behave. It's so simple that one list gets shorter, the other one is getting longer. But if the one gets used up, the other one gets reversed and put the first one, and it's going on and on and on and on. So I think this is the sole part of my own invention on this Erlang algorithm. I have to tell you the truth. but since the algorithm is so good, I really recommend these algorithms because these are so simple and easy to prove. Easy to prove if they are getting something wrong. So please try using them. And anyway, I also measured some brief performance values. And to get the most out of these algorithms, using Hype is highly recommended because Hype has the optimization facilities of integer calculations inside. But one bad news is that handling full 64-bit numbers on a 64-bit machine means calculating big numbers. Too bad, but this is the reality of Erlang, because on Erlang, short integer only can have the length up to 59 bits, unsigned. 60 bits signed. It's in the manual. It's in the internal representation manual. Please do check it out. But measuring this, I was kind of surprised that on the EXS64, it wasn't so slow. The execution time was less than 2 times of random. Random means random module. And even on EXS1024, it's slower than the EXS64, but it's approximately the same as the twice as random. So regarding the output, it's getting longer from 43 to 64 bits. The speed penalty of those Xorshift algorithms are what I think the speed penalty is worth being paid for. So this is not the final suggestion. I think there are many more different perspectives on PRNGs, but these are suggested purposes for the alternative PRNGs. SFMT Erlang has already been used by many people, and especially I'm so happy that Kostis Sagonas proper can choose SFMT as an algorithm for the property test. And for TinyMT Erlang, I've calculated 268 million polynomial parameters when I was in Kyoto University, running this, okay, 5 minutes, running 10 minutes, okay. Running the 32 cores of a server. No, I'm sorry, 16 cores of a server for 32 days. But so you can feel free to use that. It's on GitHub. It's a huge archive, but it's on GitHub. So, and for EXS64, I think this is pretty useful as a replacement for a random module or AS183. And for EXS Plus, this algorithm does not gain much from EXS64. But if EXS64 has some sort of deficiency, you can try this, EXS Plus. And for a very long period, if a very long period is needed, maybe more than 200 bits or 300 bits of integer number, EXS 1024 is a very good choice. Okay, this is the last topic about merging them to OTP. I think this is the hardest part, and it's a work in progress. Dan Gudmundsson offered me that to use my implementation for OTP recently, actually on January. And first, licensing issues, as always. And about EXS stuff, these are public domain, and my implementation, I just put the MIT license. And I have no difficulties on relicensing it on whatever license to our own people. And I had to ask for permission for all the inventors of SFMT and the TinyMT about relicensing this to our own people with their own license. And I'm saying their own license, and vaguely, just because recently Kenneth Lundin told me that our own public license is going to be APL2. You're not laughing. This is seriously. Our own public license will be ditched from the OTP 18. So it will be APL2. And the change was after I made this slide. So sorry about that, but that was, so anyway, the license is cleared. Dan and I talked over the email a lot about this. And it was expected to be called as new random. Dan worked hard about that. But as a final decision, OTP team said no, random should be as is for the backward compatibility. Well, that is a wise decision. So it's renamed into RAND. I don't know if the name will be kept the same, but RAND is a new routine, new module. And I've given a different project name called EMPRNG for Erlang's multiple PRNG. You can pronounce it EMPRNG or MPRNG or something like that. And it has all the random compatible functions built in, which is switchable just given an atom to a certain function, so that the internal state will be changed, actually represent one atom, each of the algorithm name. And the big difference is that the default algorithm is EXS64. Okay. So what about the future directions of this, my random number stuff? Okay, I'll keep promoting banning and deprecating the good old random module for all the reasons, all the possible reasons, and use something else that is much better. If you have your own project, try using EXS64. Some other Erlang people have already done by themselves, and they have gained very good results. And merging EMPR and G2 OTP, this will be much difficult because I have to write a lot of tests. Without tests, there will be no release. So, and there will be Dan has proposed me quite a few enhancement proposals, such as more algorithms or user surprise functions. And last but not least, analyzing the performance implication of large-scale applications of these new algorithms is necessary. I'm worrying if the NIF-based SFMT could crash React if React is using SFMT. This is a serious concern. So if you have any bad experience on using these algorithms, please do let me know, so that I can take care of it, or I can get work around it for that. So thank you very much. That's it. Okay? All right, questions, Fred?
At some point in the talk, you mentioned choosing the period we need for these random number generators. How do I go about picking or knowing what kind of period I need for a number generator?
What kind of what?
Period. So is it 2 at 64, 2 at 119, or whatever the period, the time it takes to repeat the cycle in the number generator?
Yeah.
How do I choose that?
That's a very good question, because when you even okay, the question is that how do I choose a period length or period itself? And it's really hard. Hard means even if you see there's a book called The Numerical Recipes for NC, and the author says 2 to 33, 2 to 64 is enough. Enough for what? They don't. And Professor Vigna says, Xorshift inventor, also says that longer period does not necessarily guarantee a good random number. I think he's saying this from his observation from the test results. But generally speaking, his rule of thumb for Xorshift is that 64 is enough for daily use, such as replacement for random or rand routine or something like that. 1024 will be sufficient for almost all possible physical or maybe algorithm simulations. And he also gives 4096 version of the Xorshift star. And he says that's an overkill. That's what I can say.
Aren't there FIPS 140 minus 2 tests that you can run? These are sort of automated regression tests that you can actually run those tests through, and it could also help in identifying the period. Okay,
the question was about the proposal of running a FIPS 140-2. Yep. That's right. It's a regression test. Whether putting it in earn OTP process, whether you can put it in earn OTP testing process, that would be. I don't know whether it would be possible, but I think it's a good proposal, because that kind of a testing should be needed for any kind of random number generators, I think. And lots of people have their own Xorshift-like proposals. Recently, there was a proposal on Twitter sent to me from Roy Kogan on the matter of a Cowboy. A Cowboy web server. He told me that there's an implementation called PCG. And Dan Gunderson also suggested me there's an implementation called Jigrad. And there are lots of those implementations, because it's about how scrambling, how a better way of scrambling is discovered. So I think your idea is good, but I don't know whether OTP team says yes to that. Did I answer your question?
Yep.
Okay. Okay.
So is this already optimized? For example, I noticed once that bit shifting left is slower than multiplying by 2 sometimes.
Actually, these are not fully optimized. Okay. The rule of thumb in Erlang. Okay. Well, his question was, are they really optimized? And I said no, because the rule of thumb in the Erlang community is that you have to make it work first, and make it profile, then optimize. And I'm thinking about the same thing like you do, because bit shift or word length, especially of the short integer limitation of 2 to 60 or 2 to 59, that will affect the overall performance a lot. But that is for future work. So I think the time is over.
All right, thanks again, Kenji.
Thank you very much.